This conference will now be recorded.
Okay, we're looking at some extra examples from the Unit 3 notes, kind of going through each of the sections and seeing what we've kind of skipped over. I could not remember if we had done number 4, so from section 3.4 to 3.5, so I'm going to do that one first just in case. So it says find the production level that minimizes the average cost per unit for the cost function, and they gave us the C function here, where C is the cost in dollars of producing X units of a product. So our first step here is to find the average cost equation, because they said we're minimizing that. So remember, that's when you take your C and you divide everything by X to make it C bar. So that makes this X squared minus 8X plus 24. So remember, C bar is C divided by X. Then to minimize, we need to take a derivative of C bar. So C bar derivative would be 2x minus 8. We set that equal to 0. That gives us a critical value of 4, because we'd add 8 and then divide by 2. So 4 units, we want to test real quick to make sure that it actually does minimize the average cost function. So if we put 4 here and plug in maybe 1 and 5, plug that into the C bar prime. So if you plug in 1, you get a negative sign, but if you plug in 5, you get a positive sign. So notice that is a min. So 4 units produced would minimize the average cost per unit. For this production level, show that the marginal cost and the average cost are equal. Okay, so remember, marginal cost is when you use the derivative of the original function at a value, and average cost, remember, is C bar. So when we take the original function and we take the derivative of it, that would be 3x squared minus 16x plus 24. We know that C bar, we already did this from before, was x squared minus 8x plus 24. And what we want to do is we want to show that for 4 units, marginal cost and average cost are exactly the same. So we're plugging in 4 for both of them. So over here, this is 3 times 16 minus 64 plus 24. That is 48 minus 64 plus 24, which gives us a marginal cost of $8 per unit. Okay, and if we plug in 4 over here, this would be 4 squared minus 8 times 4 plus 24. That is 16 minus 32 plus 24. That is going to also be 8, and that would be an $8 average cost per unit. So when you have the minimized average cost production level, that's the same as finding the marginal cost. We want to sketch a graph for the average cost function. So let me get a thinner ink for this. There we go. Excuse me. So if we want to sketch this, we have C bar was x squared minus 8x plus 24. We can plug in some x values. 0 would be 24. If we plug in maybe 2, that would be 4 minus 16 plus 24, so that comes out to 12. I also plugged in 4, so I just did this on my calculator, 6 and 8, just to have some symmetry here. So when I plot this, I counted by 2, 4, 6, 8. And then I chose to count by, I believe, 4s over here. So 4, 8, 12, 16, 20, 24. So 0, 24, 2, 12. So this is 4, 8, 12, 4, 8, 6, 12, and 8, 24. Now notice I'm going to extend it on this side, but I didn't go further over here because you can't produce less than 0, or you can't produce negative units. So that shows us that that minimum happens at 4 units that we produced, and the minimum value was $8 for cost. Okay, so then I believe we did 5 and 6. I didn't mark either one of those, but I think we skipped number 7. So it says a commodity has a demand function modeled by P equals 80 minus 0.2x and a total cost function modeled by C equals 30x plus 40, where x is the number of units. We want to know what price yields a maximum profit. So the first thing is we have to have a profit function, then we have to maximize it, then we have to go back and find the price. So this is the demand function. So remember, revenue is x times P. So revenue is 80x minus 0.2x squared. We need that because to get profit, you need R minus C. So that would be 80x minus 0.2x squared minus 30x plus 40 in a parentheses. So my profit function is 80x minus 30x. Well, let's get the leading coefficient first. So negative 0.2x squared plus 50x minus 40, because you're distributing that negative. And then we want to take p prime to find the maximum. So that's going to be negative 0.4x plus 50. Set that equal to 0 for a possible extreme of value. So that's 0.4x equals 50. Divide both sides by 0.4, and I get 125 units. Now, they didn't ask us for how many units should they producing to make this a maximum profit. They asked us for the price that yields a maximum profit, but you had to have units to do that. So we need to plug that back into the P function. So P equals 80 minus 0.2 times 125, and I got that that price should be $55 per unit. So let's double check that. Let me get my calculator. Just because I did this a few days back, just double checking to make sure we got the right answer. So 80 minus 0.2 times 125. Yep, that's $55 per unit because that's our price. When the profit is maximized, so that means when we have our optimal number of units, which is 125, what is the average cost? So to find average cost, we need the average cost formula. So 30x plus 40 all divided by x. It says we're just plug and chug. You don't actually have to reduce this because we're going to be plugging in the number of units, not the price. Okay. So we need to do 30 times 125, then add 40 to that, and then divide it by 125. So I'm getting that that comes out to 30.32. So this is $30.32 is the average cost per unit when we have a max profit. All right, and I believe we did 8 in class. So that moves us on to section 4.1. We did most of 4.1 in class together. I believe that I had marked one thing. Did I mark? No, we did all of 4.1 in class together, I think. If you guys have different results in your notes, let me know, because I did not mark anything in 4.1. But in 4.2, I did mark that we needed to do number 9. That's the one we skipped over. So let's do number 9. It says you want to invest $5,000 in a certificate of deposit for 12 months. You're given the options below. Which would you choose? Now, if they hadn't thrown in continuous compounding, you could have converted all of these to an effective rate and just said that the one with the, if you're investing, the one with the highest effective rate would have been great. But you don't really have a way to plug continuous compounding into the effective rate formula, since it's not, it's an infinity amount of compoundings essentially. So we're just going to plug these in and just use what we have. So the formula for compounding quarterly or monthly is this one. So we have $5,000, 1 plus 0.0525, because I'm doing A, divided by quarterly compounding, so that's 4. And then this is 12 months, which means for 1 year. So time is in years, so it's actually just going to be 4 times 1. So let's work that out on our calculator. So 0.05, I have to work mine out kind of inside out, since this calculator is a little funny. Plus 1 raised to the 4th, and then times by 5,000. That's 5268. Let's just round to the nearest whole. Okay, For B, we're going to do a different rate and compounding monthly. So 5,000, 1 plus 0.05 divided by 12, 12 times the 1. Now notice they did compound more, but they significantly lowered the rate by 0.25%. So 0.05 divided by 12 plus 1, and then raise that to the 12th, times it by 5,000. That's 5,256, which is lower. So it's not as good of a deal. And that really shows us that the number of compoundings does affect stuff a little bit, but not as much as your interest rate. The interest rate is key. And then continuous compounding with 4.75, that would be the PERT formula, which is 5,000 times e to the 0.0475 times 1 year. So 0.0475 needs to be the exponent on the e, and then times it by 5,000. That is 5,243. Now, if I was taking a loan out, I would want that one because it's the lowest. But since I'm investing, I want the best deal, which gets me the most money. So I would go with A. Okay, and then we got into 4.3, and we got through all of the first page, and then remember we did all the B parts on the second page. So I'm going to go through and do all of the A parts. This says find dy dx implicitly, so that means with respect to x here. This first one is a product rule, so over here I'm going to do some scratch work. So we have x and e to the y are our two functions. If you take the derivative of x with respect to x, that is 1. If you take derivative of e to the y, it's e to the y because it's always itself, but you have to chain on the derivative of the inside with respect to x. So derivative of y is 1, but because it's not an x, we have to tack on the dy dx. So then for this first part right here, it's going to turn into 1 times e to the y, so e to the y plus x times all of this. So x e to the y times dy dx. Then we keep going. Take derivative of minus 10. That would just be x. That'd be minus 10. No dy dx needed. Derivative of 3y with respect to x would be 3 dy dx. And derivative of 0 is 0. Okay, so we want to get all our dy dx's on the same side. I'm actually going to move over the ey and the negative 10. So I have x e to the y times dy dx plus 3 dy dx equals 10 because that got added over, and then minus e to the y. Pull out the dy dx. That would leave me with a parentheses x e to the y plus 3 equals 10 minus e to the y. And then I divide by the parentheses. So dy dx is 10 minus e to the y over x e to the y plus 3. And again, this is, remember, a generic form using both x and y from the ordered pair of a point on our function to find the slope of the tangent. All right, let's look at a part on this one. It says find the second derivative. So we need to take two derivatives. And this is not with respect to anything but regular old x. So y prime equals, this is 2e to the 3x because it's itself right there, and then you times it by the derivative of the inside, plus 3e to the negative 2x times the derivative of that inside, which is negative 2. That makes y prime 6e to the 3x. 3 times negative 2 would be negative 6e to the negative 2x. To take a second derivative, we need to do the same thing. So 6 e to the 3x times the derivative of the inside minus 6 e to the negative 2x times the derivative of the inside. That's going to be 18 e to the 3x plus 12 e to the negative 2x. And those do, I mean, you could pull out a 6 as a common factor, but the e's don't have a common factor because they're different exponents. Okay, for number 4, we need to find the equation of the tangent line for the described function and the point. So first thing, we're going to take the derivative of this. So f prime of x equals 2 e to the x, and derivative of the x is just going to be 1, so it's itself. And then we would plug in 1. Remember to find the actual slope. So f prime of 1 is 2e to the first. So it's just 2e. So my slope is actually got the e in it, which is okay. E is just a number. So then we go to do this point slope. We would have y minus the 2e, that's its y value. And then our slope is also 2e. And then we have x minus 1. So this is y minus 2e equals 2ex minus 2e. When I add over the 2e, it cancels out on both sides. So this is my equation. But you have to remember 2e is a numeric, excuse me, my throat's really bad. It's a numerical value, so it's some kind of decimal. Okay, just to kind of get us ahead, I'm kind of looking at the last page that was on this section. I'm going to go ahead and do 5, and that way we can skip it when we get into class. And then we'll do 6 together in class because it's a little different. So this one is a demand function where the price is not based off of a linear equation or a quadratic even, it's based off of an exponential. And it says where P is the price in units and dollars and X is the number of units. So this is tying back to what we did in the last units. So it says what production level will yield a maximum revenue? So remember, we have to find the revenue equation first before we can do that. So revenue is X times P, which in this scenario would be 50x, because we're just going to times it by what's in front of that e to the negative 0.1234125x. So I had to count 4 zeros there. To get a maximum revenue, we need to take a derivative of that. So r prime, okay, because there's an x out here with the 50, that means this is a product rule. So I have 50x, which is derivative of 50. I have e to the negative 0.1234125x. So notice those are 4 zeros. I just counted them. And I need to take the derivative of that. So it's going to be the same, it's going to be same e to the x, but you're going to times it by that big old decimal for the chain rule. So I'm going to bring that to the front just so it's easier to see it. And that's really long to write. So then to do our product rule, we have to cross those. So this is 50 e to the negative 0.0000125x plus, and then it's 50 times this decimal right here. So 50 times 0.000125, and that's negative. And that's going to be 30625. So negative 0.000625x, because that x right there, and then our e to the negative 0.0000125x. So the hard part about this problem is just saying all those zeros. Okay, so this is our derivative, and I would probably factor out the e's because they're exactly the same. So r prime is e to that negative 0.0000125x, parentheses, 50 minus 0.000625x. Now, here's the interesting thing. This will never be 0. So it can't have a critical value there. I know this is negative and you think, oh, it's going to give me something where it goes negative. But remember, negative exponents don't make you have a negative answer. They just flip a fraction. So the only thing we have to solve to get a possible production level critical value is this equation. So 50 equals, because you'd add this over 625x, divide by that, and I believe I got 80,000 units. So it's a big number. That's because you're dividing by that really small decimal. So that's the production level. They didn't ask me for the price yet. They said, what was the production level? That's the number of units. The next thing they ask is, what is the price at that production level? So that's where you take 80,000 and plug it back into the little p formula. So that would be 50 e to the negative 0.123, 4 zeros, then a 125 times 80,000. So let's get our calculator. So 80,000, not 82, times 0.1234125, and that's negative. That's an exponent of negative 1. So this is 50 e to the negative 1. So let's finish working that out. So take e to that power times it by 50, and we get $18.39 per unit. That's what they should have their price set at to get that maximum revenue. And then what is the max revenue is asking you what is the actual Y value associated with that. So you have to plug back into your revenue equation. So this would be 50 times 80,000, because we're using R for this guy. And then that would be times e to the negative. We already know that's going to come out to -1 because we just did it, because that guy was from right here. Okay, just saving myself rewriting all that. So let's do that. So e to the -1 times the 80,000, oops, times the 50 that was out front. So that's 1,471,518 if we round up. So 1,471,518. They could ask you to round to the 2 decimal places. You just have to read the directions. I don't remember if this one did. They didn't specify, so I'm just going to round to the nearest dollar. Right, so notice this is the same process as we've been going through. It's just the functions are a little bit more interesting, and you have to know how to do the derivative of the exponential. So that leaves us just number 6 to finish up that section, and then the rest of Thursday's class will be focused on logarithms. All right, have a good day.